Lesson 8, Day 2, Identifying Linear Functions. Let's explore the idea. Graphing is one way to tell whether a function is linear. Use the equation y equals 2x plus 1 to complete the table of values. Then use the table of values to make a graph. Does the equation y equals 2x plus 1 represent a linear function? All right, let's go ahead and plug this in. Now remember on day 1 we said that when you have your equation in the form of y equals mx plus b and you didn't have your x value be raised to any other exponent bigger than 1, like if you had x squared, x cubed, or anything of the sort, that would be non-linear. But when it's just an x standing alone, then that is linear. And we'll be able to prove that right now. Alrighty, let me move this out of my way so we can actually do that. So keep that in mind. Alright, so again, our equation is y equals 2x plus 1. So we just plug in our input values and figure out what we're going to get for our output. So y is going to equal 2 times negative 2 plus 1. Well, 2 times negative 2 is negative 4, plus 1 is negative 3. Same for the next one. Y equals 2 times negative 1 plus 1. That's negative 2 plus 1, which is negative 1. Then we have for 0, 2 times 0 plus 1 is just 1 because 2 times 0 is 0, plus 1 is 1. Then we have 2, I don't know why I keep doing that. 2 times 1 plus 1 is equal to 3 because 2 times 1 is 2, plus 1 is 3. And then finally we have 2 times 2 plus 1, which is 5. All right, and then we're just going to go ahead and graph these. So we have negative 2, so we start at our origin, move left 2, move down 3. Then we have negative 1, start at our origin, left 1, down 1. Start at our origin, stay at the origin, up 1. And then we have 1 comma 3. So let me go ahead and write these all to the side so you know what I'm talking about. So we have negative 2, negative 3, negative 1, negative 1, 0, negative 1, 0, positive 1, 1, comma 3, and 2, comma 5. All right, so now I'm at 1 comma 3, so I started my origin, which is 0 comma 0. I move right 1, up 3. And then finally, I started my origin, I move right 2, up 5. And I go ahead and plug that in. Oh, I made that look crazy. Okay, it doesn't want to go through the line, but yay, okay, much better. So I'm happy with that. Alrighty. So again, is this a straight line? Yes, it is. So this is a linear function. So again, I already knew it was going to be linear because we had y equals 2x plus 1. And because my x or my input looked like that with just an x, not raised to a second power, third power, anything like that, it was going to be linear. And I know I proved that it's linear because our line is a straight line, or our graph is a straight line. So it's definitely linear. Okay? Completely linear. All right, and I move on to number 3. Use the equation y equals x cubed to complete the table. I know for a fact x cubed is going to be nonlinear because my x or input value is not constant. It's continuing to change. Okay? And I can go ahead and call it and say this is going to be non-linear because my input is not constant. Well, it won't produce a constant rate of change. Okay. And we'll be able to prove that in just a second. So with this, let's go ahead and do this. So we have y equals x cubed. So our y is going to equal negative 2 cubed, which is negative 8. Then negative 1 cubed, which is negative 1. 0 cubed, which is 0. 1 cubed, which is 1. And 2 cubed, which is 8. So my x's, they all increase by 1 every time. So that part is correct. But then what ends up happening is if I move this over and make the same type of comparison from one y value to the next, I go from negative 8 to 1. I increased it by 7. I go from negative 1 to 0. I increased it by 1. I go from 0 to 1. I increased by 1. And I go from 1 to 7. 1 to 8, and I increased it by 7. There is no constant rate of change. That's what I'm talking about. So there is no constant rate of change. And then I can go ahead and further prove that by, let me make that smaller. And I'm going to further prove that by going ahead and graphing this to prove it to you. And I'll go back up to the top to let you see what I'm talking about. So I have 2 comma negative 8. That's my first set, my first order pair. So I have negative 2 comma negative 8. I have negative 1 comma negative 1, 0, 0, 1, 1, and 2, 8. So this is what this one's looking like. That is clearly not a straight line. So not a straight line, and that means it's non-linear. So let me prove to you that because I saw immediately that our first example in number 2 is going to be linear, I knew that just by looking at my input in the given equation. So I knew that, and let me prove to you how I knew that. Or let me prove to you how that's correct. So then, again, in order for it to be linear, it needs to have a constant rate of change. So again, my x values are always increasing by 1. So to get from 1 to 2, add it 1. 0 to 1, add it 1. But then I go for my y's, negative 3 to negative 1, add 2. Negative 1 to positive 1, add 2. Continue adding 2. So I know how to get a rate of change is my change in y over my change in x, and that's going to be 2 over 1. So I get a constant rate of change of 2. But if I try to do it down here, sometimes I'd have a rate of change of 7 over 1. And then I'd have a rate of change of 1 over 1. You can't do that. That doesn't have a constant rate of change. It changes. It could even change even more if I kept adding on values like negative 3 for x and positive 3 for x. Then I'd have it at 27 and negative 27. That's totally different. It just continues to jump. And we're not trying to do that. We have it adding up by like 19. We're not trying to do that. Okay, and then it continued to add up by 19. So then we could have another rate of change of 19 over 1. There's nothing consistent about this rate of change. Okay, that's what I'm trying to show you. So again, you can look at that equation and know for a fact this is going to be a straight line because my input is constant. I know it's constant. It's not going to be, my input is going to always be my x, and I'm not going to be putting it up to any different exponent. It's just a standalone x, so I know it's going to be linear. Okay, and if it's anything like x squared, x cubed, or anything of the sort, then it's nonlinear. Okay, I know it's a little confusing, but with more practice, you'll understand where I'm coming from. All right, moving on to our next page. All right, so let's talk about it. Let's summarize all this stuff. Analyze the functions you've seen so far in the lesson and complete the chart. So we have our function of y equals 4x. We had an initial value of 0, and we talked about that one on day 1. We had a rate of change of 4, which is our coefficient, of course. And then we have the equation form y equals mx, of course. Is that linear and nonlinear? And I'll just have L for linear. Then we have y equals x squared. Remember, we're going to go by the y equals mx plus b, where m is going to be our rate of change and b is going to be our initial value. Okay, so for our function, our second function of y equals x squared, we have no plus b. So our initial value there is 0. Rate of change is going to vary because we have x raised to the second power. The equation form here is going to be y equals mx squared, and that is going to be non-linear. All right, then we have our next one is y equals x squared plus 2. So we have an initial value of 2. And then, of course, our rate of change is going to vary because we have x raised to the power of 2. So it's going to vary here. Our equation form is going to be y equals mx squared plus b, and of course that is non-linear. Then we have y equals 2x plus 1. Our initial value is 1. Our rate of change is 2 because that's our coefficient. And then our equation form, it does have the equation form of y equals mx plus b. And is that linear or non-linear? It is going to be linear. And finally, y equals y equals x cubed. So the initial value is going to be 0 because I don't have anything added or subtracted from our x or input value. Our rate of change is also going to vary because x is raised to the third power. The equation form is y equals mx cubed, and that is nonlinear. So what you notice is if it can take the form of y equals mx plus b, like our first or our fourth example, then it is linear. And even though it just says, I said mx plus b, this one is still mx plus b, the first one. The only thing that we have to understand is that since it doesn't have anything there, we can just add a 0. If there's nothing there, just add a placeholder 0. That was our initial value anyway, so you can still add 0 there to technically have that mx plus b. Okay. Number 5 says, look at the chart in problem 4. In the equation, y equals mx plus b, does m represent the initial value or the rate of change? M is always the rate of change. What does b represent? B represents the initial value. And y. The answer to y is that to find the y value for any x value, you multiply the rate of change by the x value. If the initial value is not 0, you have to add the initial value by multiplying to find an ordered pair. So that's what you could have put. You could have put that to find the y value, for any x value, you need to multiply the rate of change by the x value. If the initial change is not 0, you have to add the initial value after multiplying to find an ordered pair. Okay. And number 6, according to your observation so far, what equation form or forms define a linear function? That's what I talked about earlier. We could have y equals mx or y equals mx plus b. And why do you think this is so? So in both equations, the amount y changes compared to the amount x changes is always the same. So in both equations, the amount y changes by perfect. All right, and then finally, try it another way for this day. So work with your group. Yep, let's go ahead and review these. So grab each equation on a separate sheet of paper and describe your results. So we're predicting if it is a linear function or not. So I'm not gonna graph them. You can graph them, of course, and you should have. But with me, I'm just going to say whether or not these are linear functions and how I know. So I know all I have to do is look at the relationship between the x and y, or the input and output values. So I can look at my input values and I can see that for number 7, it's just an x standing alone. So to get from an x to a y always, I'm just going to multiply my x by 0.5 and then add 2. So I should have the same just like we talked about in number 6, the amount y changes compared to the amount x changes should always be the same. So I would do that. So, because my x value or input because it is not raised to an exponent, then it's linear. But really it's because it takes the form of y equals mx plus b. Okay, y equals mx plus b, not mx cubed. That was one that was not going to be linear. Remember we talked about that in number 4. Okay, and if I wanted to graph that, then I needed my points for it, so I could go ahead and do that. I could have my x's and my y's, so I could have x equaled, let's have -1, 0, 1. Let's see. So if I had my x equal -1, then I would do 0.5 times -1 plus 2. Well, that's -0.5 plus 2, which is 1.5. Yes? And then I'd have the next one, which is 0.5 times 0, which is 0, plus 2, it's just 2. Then I would have my 0.5 times 1, which is 0.5, plus 2, which is 2.5. So then I'd be able to start seeing what's happening. So every time I'm going to increase, or to get from one y to the next, I'm going to add 0.5 and continue doing that. So I have a constant change in y, and I'm going to have the exact same thing in x, just adding 1 and adding 1. So my constant rate of change, of course, is 0.5 because that was my coefficient. So I have a constant rate of change. That lets me know I'm going to have a linear function. Okay, and when I graph it, I should see it's going to be a straight line, which if I do that here, let's just do it here. And if I have -1, comma 1.5, let's just have these go, 1.5, so 1, 2, 3, -1, -2, -3. Okay, so -1, 1.5, and then I'd have 0, comma 2, and 1, comma 2.5, and when I connect them, I'd have a straight line. That's what they're talking about. Okay, so you could go ahead and use what we know, like it has the form of y equals m plus b, mx plus b, which is our linear equation form. We know that our input value is not raised to an exponent, so it makes it linear. Then when I input all of my values into a table, I see I have a constant change from x compared to y. So that gives me a constant rate of change. And then lastly, my graph, once I graphed everything out onto, and on the graph, but I noticed it was a straight line, so of course it was linear. Number 8, I could do the same thing and just go ahead and start off with a table. So I could have -1, 0, and 1 again. Okay, so if I did that and I put in 0.5 times -1 cubed. -1 cubed is -1 times 0.5 is just -0.5. Then if I have 0.5 times 0 cubed, it's just going to be 0. And then if I have, I have to do this. Let me do this a little better. All I need to do at this point, I'm just going to erase this. If you needed any of this stuff from the previous problem, just go rewind it so you can see what you missed. All right, so let me continue. Because it's going to look very similar, but it's not. And then if I have 0.5 again. But then if I extend it and go to 2, if I go to 0.5 times 2 cubed, I'm going to have 2 cubed is 8 times 0.5 is going to be 4. And that's where my problem lies. So here it seems like I'd be adding 0.5 every time, right? But then I get from here, from 0.5 to 4, I've actually added 3.5, and that is not a constant change for my y's. Yes, my x's, I've added 1 every time, but if you don't have the same thing happening over on the y side, then it's not a constant rate of change. Okay? It is not going to give you the same outcome. They're going to be different rates of change. When you have different rates of change, then that means it's non-linear. Okay? So again, from here, once I continued adding on x values, I started getting different changes in my y's. So I'd have different rates of change. And if I have different rates of change, that means that that this equation or function is non-linear. Okay? And that is how you prove whether something is linear or non-linear. You can go ahead and draw or create a table, and then further you can graph it. I'm not going to graph this last one because I just didn't have enough space, and I feel like I've done a lot on this one. But once I graph this one, I would know it would not look like this at all. And you can go back to number 3 on the previous page. It'll look like something very similar to that. Okay, and that is all for day 2.